All right, 9.3, hypothesis testing for means. And so what we're going to be doing here is really thinking about that same phantoms idea that we just did in 9.2 when we were focused on proportions, but now we are going to focus on means or averages on here. So first of all, let's just kind of do a little flashback to chapter 8 when we talked, right? There's this thing called T and there's this thing called Z, right? So we're dealing with means on both of these, but we want to talk about what's the difference between those. So if we are going to run a T test versus a Z test for means, let's first talk about Z tests. So we're going to run a Z test if the population standard deviation is known to us first, right? And then we're going to run a t test. We'll always run t test or t interval if we use the sample standard deviation in place of the population standard deviation. Right? So that's going to be the difference between those two. And it's just that simple little trade-off, right? Because we know that Z test is for normal stuff. And we know that T is, remember, not normal, but trying to be. Right? So that's kind of the difference between these two here. So we're going to see mostly t-tests in here, but every once in a while we'll see a z-test. So we'll look at an example for each of those as we move forward. So let's move on to the next kind of thing that we're going to want to know before we get into the examples. Paired data t-test for means. So paired data is when we use the same thing twice, right? So really this word paired is really short for matched pairs. Remember, we did these matched pairs when we talked way back with experiments, right? That we use two things that match up really, really well, or we use the same thing twice, right? So let's say we use like student number 1, and we took a pre-test score, and they got a 50, and then they got a post-test score, and maybe they got a 98, right? And then we would do the same thing. So then we'd take student number 2, and let's say they got a score of 60, and then a score of 73, and then number 3 got a pre-test score of 78, and the post-test score of 75. Right? So they didn't do as well. Whatever. Number 4, they got a pre-test score of 70, post-test score of 98, and so on, so forth, right? So we just keep doing it for all the ones. So, but for paired test, when we're talking about means, we need the average, but we don't care about the pre-test score. We don't care about the post-test score. What we're going to have to do this, since we're using the same students twice, right, here and here, then we're going to need to find the difference. And it doesn't matter which direction you go with the difference, just take the difference. So if I did post minus pre, we're going to get 48. Post minus pre, I'm going to get 13. Post minus pre, I'm going to get negative 3. Post minus pre, I'm going to get 28. Right? And we just keep on going here. So now this is the group of data that I care about. So from here, I would want to find the average difference, and I'd want to know the standard deviation of the difference. And then once I know the average and standard deviation, we are welcome to run a t-test. Why? Because we're going to be using the standard deviation from the sample, right? So that's what a paired data set will look like to us, and we'll run one of those examples as well today, okay? So what are we doing here? We're going to be doing t-test or z-test for means, and they're going to look very, very, very similar to what we did for proportions. And then we're also going to run paired t-tests. Again, going to look very, 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 very similar to what we did for proportions, only we're going to need to modify the data first to get us this right here. We just need this one column of data because, again, we don't care about the pre-test. We don't care about the post-test. What we care about is the difference between the pre and the post-test to see if there's actually something here, okay? Something else I'm going to add to this while we got it up here is these always have a standard hypothesis. So these are the ones that we're going to use, at least in the AP realm. So the standard hypothesis is always going to be a null hypothesis that the true average difference is equal to 0, right? So truly what we're saying is if I took the average of this, we would expect it to be 0, right? We would see if that's true. And then the alternative hypothesis is going to be that the average difference is not equal to 0 or greater than 0 or less than 0. It is going to be based on the actual, phrasing of the question. So you're going to write this down. Standard hypotheses. Every single time we know that we're doing a paired data set, this is going to be your null hypothesis, absolutely. And then one of these three will end up being our alternative hypothesis. All right. And then again, we are going to be using the idea of phantoms. So always list your hypothesis, always list your 3 assumption checks, naming what we're doing, showing the curve, shading the curve, showing the t or z score in this case, obtaining a p-value, making a decision, and summarizing finally. All right. Or remember the big ones that we need to do is phantoms. Right. Those are the ones we need to show. The n and the p are there for us to just be able to verify and know what calculator function we're going into. All right, go ahead and grab your calculators, and let's move into the next question that we have here. All right, example number 1 here. 25 high school students complete a preparation program for taking SAT test. Here are the SAT scores from 25 students who completed the SAT prep. So they give us the actual 25 scores right here. So n equals 25, okay? And then it goes ahead and tells us the mean of these scores is 500. So here I'm going to write it a little bit differently. The mean is 536. That's this. If you actually put those into your calculator, you'll find that it is 536. We know that the population average of SAT scores is 500 with a standard deviation of 100 and has an approximately normal distribution. Okay, so this is going to be all important to us. Those are some great facts. Thank you for giving us that. Run a test at the 5% significance level to determine if the group of students score better, okay, there's a key word, better than the population average due to the preparation class. Okay, so here we go. Let's think phantoms as we run this test. So when you hear run a test, I want you to always think phantoms. All right, so let's talk about this. What is the population parameter that I'm really worried about? I want to know the true mean score of all students who took this preparation program, right? So they took 25 but I want to know what is the true mean of all of the people who took that, okay? But all right, let's jump right into null hypothesis. Okay, before I actually do this first, I want to think, is this going to be a Z test or a T test? Because I do know that we're doing a means test, right? So it's because I see the word average, I see the word mean, here's another word, average, and here's the word standard deviation. Anytime those are dead giveaways that we're doing a population mean problem, not a proportion problem, all right? So null hypothesis, let's go ahead and do this. Let's say that they know that the mean is equal to 500, okay? And then alternative hypothesis, the mean is, what do they say, better. Is this group of students, the mean of this group of students is better than 500, all right? Sorry, I actually did not finish my initial thought. Is this a Z test that I want to run or a T test that I want to run? So what's the one thing that we're looking for a Z test? I'm looking for, do they give me the standard deviation of the population? If they do, run a Z test. If they don't, you're going to have to use the standard deviation of the sample in the place of. So here is the key to this entire thing is they said with a known population standard deviation of 100, we will be running a Z test on this thing right here, right? So we're going to be running a Z test. So just know that as we get into this next piece, which is the assumption piece, we need to think about a z assumption. So let's list through the assumptions. Number one, am I allowed to use a normal curve, right? Now, typically we want n to be greater than or equal to 30 for the central limit theorem. But guess what? That's not the case because n is less than 30. So then for a normal curve, then we're going to see, is the population approximately normal or normal? So I'm just going to say population is approximately normal. It says it. Look right here. Approximately normal distribution. Perfect, right? So they have given us the right to use a normal curve for our test. Number two, we need to make sure that it is a random sample. So, you know what? They don't actually use the word random in here. So if they don't use the word random, you know what we're going to say? Assume random sample was used, right? So I'm going to have to take on an assumption, which is where it gets the word assumption checks from. All right, number three. Since we're taking 25, we're going to say all students in the prep program. Do we believe that there's more than 250 students in the prep program? That's 25 times 10. You know, I'm going to say we're going to have to take a safe assumption on that one. All right, so there we go. I'm going to go ahead and put my n part of phantoms here. And I'm going to say I am going to run a z test for means. And we're doing this at the 5% level. Right? Z-test for means at the 5% level. And again, why are we doing a z-test instead of a t-test? It's because they gave me the standard deviation of the population, so I get to run a z-test on that. Okay, moving on, t. So here we go with a curve set up. That's a normal curve. Why? Because I was allowed to, based on the population being approximately normal. It should be centered around the claim, or what we know, right, as 500, right there. What we're now going to interject in here is, where is my sample? So the 536, right, the 536 that came from my sample, and we always shade more extreme. And again, based on this, we are doing a one-sided z-test. And I am only going to shade this one side over here, the z-test on that. Okay, let's continue on. Let's find the z-score. Z-score is my number, 536, minus the claim, 500, over, now we need the standard deviation of the sample here. So we're going to use 100, which is standard deviation of the population, divided by the square root of n, which is 25. So here's a small interjection that you want to use. Remember that your standard deviation for a z-test, what goes on the bottom of that z-score, will always be standard deviation of the population divided by the square root of n. This is what we did also in Chapter 8. Standard deviation, if we're doing a t-test, is going to be standard deviation of the sample, because we're going to use that in the place of, or the square root of n. Notice how they look very, very similar to each other, right? Standard deviation z-test, standard deviation t-test. The only difference is, what is the thing that you use on top? That changes it. Okay, so coming back to this, we use samples, or the population standard deviation, because we had it. So then I am going to find this number, but also remember, I'm going to do this in my calculator just like I did proportions. So I'm going to let it give me a p-value at the same time. So you ready to do this? Here's what I'm going to put into my calculator just so that you know. I'm going to go to my stat button. Then I'm going to go to my test button. Then I'm going to go to z-test. So there's actually a function called z-test. So go there with me now. Stat, test, z-test. I have stats to put in. Sometimes if you have data, you can actually put in all that data if you want. But I'm just going to put stats since I have all the numbers I need. So the first thing it says is mu with a subscript 0. So they're literally saying, what is the, so you could put a little subscript 0 here and a subscript A here if you wanted to. So we're saying the null hypothesis mean is 500. What is your actual standard deviation of the population? Notice the symbol that they give you. So that's going to be 100. The X bar is going to be 536. Sample size is 25. And I want a greater than sign there. So let's calculate that real quick. So I'm going to come back to this. Z equals 1.8, and I guess I could put a 0 on the end if I want to. P-value is equal to 0.036. All right, there we go, right there. If you go back to stat test z-test, go all the way down. Notice then you have two options here. One says calculate, one says draw. Go ahead and do the draw button, if you will. Check out what it does for you. It literally draws the curve that we just did right here, right? It draws that curve. So it gives you the stuff. So if you had no idea what to draw, just hit the draw button. It'll tell you what to draw. All right, here's where you really got to be the stats person, because now we have to make a decision. Let me just remind you real frankly, how do we make a decision? If p-value is less than the alpha value, then reject the null hypothesis. If the p-value that we get happens to be greater than the alpha value, then we fail to reject the null hypothesis. Right? So it's going to be one of those two. That's your decision that you're going to make here. All right, so what we do, we come up and find the alpha level, which is also known as level of significance, which is 5%. So then I'm going to look at these. I'm just going to go ahead and write this out. My p-value is 0.036, and guess what? That happens to be less than the alpha presented value of 0.05. So what are we going to do? The decision, reject the null hypothesis. All right, so that's what that looks like right there. And then let's summarize. So again, here's kind of your summary. We have significant evidence to suggest that this prep program produces an average score better than 500. And done, right? That would do it right there. So that is what we're going after, right? So again, this all started though from identifying, am I doing a z-test or a t-test? All right, once I've identified it, run through phantoms, and we got it. Okay, let's move to the next example. Example number 2. So example number 2, we're going to do the exact same idea. Now, so what I did, I just took that same thing, but now let's just imagine, if you will, that they did not give me the population. So take a look at example 1, this little statement here. We know that the population, blah, 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 blah. Example number 2, that's not stated in here, right? 25 high school students, here's their scores, gives us a mean, X bar is 536, gives us a standard deviation, S is equal to 93. So with those two right there, they do not give me the standard deviation of the population. All we have to use here is standard deviation of the sample. So what does that mean? That means we are going to be running a t-test instead of a z-test. So we're going to run a 5% significance. We're going to do all the same stuff. So let's do this. So watch, let's see what the difference is. So my hypotheses, what's my hypothesis? It looks exactly the same whether you're running a z-test or a t-test. We're still going to think that the population of this preparation students program is equal to 500. The alternative is that it is greater than 500. Okay, assumption checks. What do we do? The first one here. Now, since we are not doing normal, we're trying to test, is it a t instead of a z, n is less than 30 again. So what does that mean? We want to make sure there's no outliers or no strong skewness. So what I'm going to do, I'm going to put all this data into my calculator. So go ahead and do that. Like take this entire data set and put that in your calculator. Okay, once it's done, I'm going to go up to second stat plot, turn on a plot. Let's turn on a histogram. I'm going to go to zoom 9, and I'm going to build my histogram here, and literally just going to write it over here. So here's what my histogram looks like in my calculator. All right, kind of looks like this. Got a little slowdown here, another bar here, and a couple more here. So what I'm looking for again, do I see any noticeable outliers or strong skewness? I'm going to say no outliers, no gaps in this data set, no strong skew. It looks like a slight skew, but no strong skew. So we're okay to proceed. The t-distribution is going to work for us. All right, remember that. Remember, if it's less than 30, we got to check the actual data. If it's greater than 30, we would call it robust, and we'd move on. Again, we're going to have to assume random sample here. Okay, so we're going to take on that assumption. And number 3, 10% rule, all students in prep program. Is it greater than 250? We're going to have to take on that assumption as well. Okay, so that's what that looks like. Now, if I'm going to name what I'm going to be doing, instead of doing a z-test for means, I'm going to be doing a t-test for means at the alpha equals 5%, just like I did last time. All right, so let's build our curve. So I'm going to build a t curve instead of a z curve. Guess what? Because I'm not a great artist, they look the same. All right, so this is what it looks like. We got 500. Now I'm going to bring over my sample, plot it, and shade more extreme, right? Again, a one-sided t-test because it's greater than, so I'm only going to shade the one side of the curve right here. All right, so let's do a t-score instead of a z-score. How does the t-score look? It's 536. That should be a 6 right there, 536. 536 minus the claim, 500, divided by, now instead of doing like we did last time, we're going to have to put the sample standard deviation there, 93 over the square root of 25. So that's going to change it slightly. We're going to let our calculator find that number for us so we don't make any mistakes. Let's do a p-value of roughly something. So let's run a t-test. So I'm going to go to test, t-test this time. And now that I put the data in my calculator, I'm going to use it. 500 L1 frequency greater than, right? And then let's do this. I get a 1.94. Nope. Go back. 1.92 is what that is. And then I get a p-value of 0.033. 2 if we wanted to, right? Let's go 4 decimal places, why not? So that's what that looks like right there. Okay, let me stop here for a second. Look at what we did up here. So with using the same data, but because I was given the population standard deviation, I was able to do a z-test. And it gives 3.6%, right? At a 1.8 z-score. Remember, a t-score, a t is based on that same idea, only I use sample standard deviation there. So it gave me slightly different, right? It gives me a little more error, but they come out really, really close, right? Because this is not perfectly normal, but it's trying to be, right? That's the whole idea of a t distribution. And we'll talk about using the actual table lookup. We'll do that in class. But this right now, for the most part, let's use our calculator to help out with this stuff, okay? So that's what we got there. Now let's go ahead and make a decision. You make a decision just like you would with a z. My p-value is less than alpha, which it is. Then we are going to reject the null hypothesis. Since we're rejecting the null hypothesis, we're essentially saying no to this, and we can suggest this now, right? So that's kind of how that always works. You're just going to summarize that for yourself. So here's what we say. We have significant evidence to suggest the PrEP program produces a better average score than the national average, or whatever we're going to call that. Okay, so that's what it looks like right there. And we're done. But notice I just wanted to do these two together. Exact same data set. This one, they gave us a little extra information about the population. This one, they did not. So that's the difference between a Z and a t-test. Most of the time, we will see t-test being run instead of z-tests. But just know z-tests are always an option to do. All right, example number 3, let's do the last one together here. Toyota did a test to see if their cars were unbalanced by looking at the way the tire tread wears from one side of the car to the other. Below is the sample data from 14 different Toyotas that were the same model, same year, in order by car. So what they mean is car number 1, and this is also car number 1, number 2, number 3, number 4, number 5. Right, so we use the same car multiple times. Right, again, that is called a matched pairs design that we got going here. Right, so car 1, car 2, car 3, we keep going over and over and over again. Right, so here's the idea, as we said earlier in the notes, is that we don't care about the right side of the tire, we don't care about the left side of the tire. What we care about is the difference between the tires. So we are going to have to create our own data set here. Let's call it the difference between the tires. And I'm going to do left tire minus right tire. Right, so this minus this. So if I do that, it's going to give me certain values, right? So then I'm going to get a difference of 12, a difference of -2, a difference of -2, a difference of 3, and so on, right? So I'm just going to keep going down the list here until I get all the different values that I need. Because then I'm going to use this data set here in a second and put this right into my calculator. Now notice some of the values are negative, some are positive. That's okay, because what we care about is the average between those. Okay, now that we have the difference data set, let's use it. Okay, so I will be running a t-test. Why? Because look in this entire statement. Do you see them project for us the standard deviation of the population of differences? I don't either. So what we're going to do is let's get right into understanding that this is going to be a t-test. Most of the time when it is a matched pairs design, you will be running a t-test almost 100% of the time. So just know that that is what we will be anticipating. So I'm going to put this data set into my L1 real quick, just so I have it, and then we'll work from there. Okay, so now that I got this entered into my L1, let's get right to it. Again, please only enter this into L1, only the difference. That is what we're focused on. We don't care about right or left, just the difference. All right, get right to it. Hypotheses. My null hypothesis is always a standard, right? So just like we said earlier in the notes, the average difference is equal to 0. So we are going to assume that there is no difference in the wear between the right tire and the left tire. Now we're going to see if we find enough evidence to reject that and say that there is difference, but right now, no difference. Alternative though. Okay, so here we go. Here's what we got to figure out. This run a test significance to determine if there is a difference. We don't care if it's a greater difference in either tire. We will just want to see, is there a difference? So we'll say the average difference is not 0. So now it's a two-tailed or two-sided test. Okay, so that's one of the kind of fancy statsy things that we say, two-sided test, because you're going to see when we do our curve, we're going to shade two sides. All right, here we go. Alternative. Or assumptions. Number 1, or I should do number 1. All right, we need to make sure we can use, since we're talking about a t-test, we need to be able to use the t-distribution. Well, here's what we need to do. We're going to take just the list 1, and we have it in our calculator, so let's punch it into our calculator. Let's go, I'm going to go second stat plot, and I'm going to turn on a stat plot because n is less than 30. So remember what happens if n is less than 30? We need it to shake out so that there are no outliers and no extreme values, right? So here's what mine looks like. So it really stacks up real nicely, and then there's a gap, and then it stacks over here. So I don't like gaps. Gaps indicate that there could be some type of outlier, but look at the shape of this thing, right? It's really taking on a nice shape, right? So I'm going to definitely say no major skew. Possible outlier, use caution. Now we can avoid anything else because we're telling them use caution right here. So we're making an assumption that there is no outlier. A gap does not necessarily mean there's an outlier. It does, though, make me pause for a second, say, possible outlier here. Okay, but let's move on because we're going to assume that there is no outlier and move accordingly. Okay, so as we keep going, next thing we need a random sample, right? So below the sample, 14 different Toyotas from the same model, same year. So we're going to say assume random sample. All right, so we had to do this earlier. There's some assumptions. That's why this is actually an A. It's called assumption checks. And let's just say that all Toyotas of this year / model. I hope they made more than 140 of these cars. Probably, that's a safe assumption. All right, T, what am I going to be doing? Oops, sorry. E, N, what am I going to be doing? I'm going to be doing a T test in my calculator for means. So it's actually, so the pair data, the only thing that makes it weird is that we have to create our own difference column if they haven't created it for us. Other than that, now we're just running a t-test for means because we're using the sample standard deviation. That's the t-test. And then we're still doing an average. All right, so let's get right onto the t. The t is draw the t-curve, which looks a lot like my z-curve. Right? We are going to center this around the claim 0. Every single time we do a match pairs, we are centering around 0. And now we're going to bring in our x bar and our s value. So let me go ahead and get those from the calculator. Here's how we do it. Stat, calc, 1 var stats. I put my data in L1, so I'm going to make sure my list says L1. Calculate. Here's what I get. I get 2.07, and I get a standard deviation of 5.225. 5.225. Yeah, let's use that one. Okay, so if I put this in there correctly, 2.07 is over here. I would always shade away, right, to the more extreme. But remember, let's come back to this alternative. It's a two-sided test. So however far you went this direction, let's go the same distance this direction, and let's shade there. So two-sided means you gotta balance this out and make the other side the same exact shading as you did this side. So be aware of that. Now your calculator knows it's two-sided when we put the right thing into our calculator. So you'll see that we don't have to like double the p-value because it will calculate this p-value and it will double it to give us both p-values together. All right, so we'll do that in a second. But let's come back over here. Let's say t equals how do we do a t-value? It's my sample, 2.07, minus the claim, which is 0, over standard deviation, 5.225, which is over 14. And again, I'm not going to actually calculate that out by hand because my calculator will do it for me in just a moment. P-value is roughly, and I'm going to let my calculator do this for me again, and then I'll make a decision based on those different things. So let's go. Let's do this stat, test, t-test. Do we want to use the data? Sure, I got the data in my calculator. So the null hypothesis is 0. The list is in L1. Make sure that you highlight the not equals to symbol, and then let's calculate. If I do that, I get 1.48. So that means you had to go 1.48 standard deviations to the right. So you're going to have to go 1.48 standard deviations to the left, right? So that's okay. That'll give us the different movement values. Now the p-value that is represented here is 0.1618. 8. Now again, I don't need to double that p-value. Your calculator's already done that for me. Now if I was going to look this thing up by hand, I could go find just the p-value for this side over here and double it, and it would give me both p-values there. But this is the p-value. All right, let's make a decision. They said to use alpha 1% level. This is definitely greater than that. So I am going to fail to reject. Again, why? Because my p-value happens to be greater than my alpha value. If your p-value is greater than the alpha value, you fail to reject. So summary, we do not have evidence to suggest that the where is different between the right and left sides of these Toyotas. Right, there it is. Because again, we failed to reject. So we went ahead and said, okay, I did not find any evidence to say no to this claim, so I'm definitely not going to say that claim. So, okay, we'll stick with this for now. Now, again, remember, we never say accept. We are always just in the mindset of I did not have enough evidence this time to reject. And that would do it. Phantoms. But think about all the different levels that we do, because as you are asked specific multiple choice questions, sometimes it's just about hypotheses. Sometimes it's just about the assumptions. Sometimes it's about calculating a t or getting a p or making a decision, right? Those are the different ideas that we need to know all about on this one here. Right? So you're going to find the same idea over and over and over again as you do these things. So just take your time, think about the different aspects of phantoms, and use your calculator like crazy. The one prop z test, the z test, or the t test. We're going to be using one of those three functions every single time in this chapter. All right?